Hidden beneath a piece of glass thinner than a quarter are temperatures and forces that reshape matter. In a single photovoltaic cell, photons strike a silicon wafer only 150 micrometers thick and trigger an invisible avalanche. Electrons freed from atoms, guided by a razor-thin junction and driven into a circuit. The challenge is simple to state and brutally hard to achieve. A silicon crystal with a band gap of 1.12 electron volts must be purified to near parts per billion. Its surfaces must be sculpted, its chemistry tuned, and its contacts printed with micron-level precision. Every photon counts. Lose it to reflection or let it recombine at a rough surface, and that potential kilowatt-hour is gone. In this chapter, we map the anatomy of a modern cell. We break down its layers: the bulk silicon substrate, the emitter formed by heavy dopants on the front, the anti-reflective coating a few dozen nanometers thick, the thin metallic fingers that collect current, and the back surface field that pushes charges away from recombining. Visualize electrons as rushing commuters, the junction as a toll gate, and the entire cell as a tiny power station that converts light into directional flow. This is a machine we will build step by step. It starts with sand. Quartz, 99% silicon dioxide by weight, is the humble feedstock that becomes the purest industrial element on Earth. The first transformation is a reduction furnace, where silica reacts with carbon at about 1,800 degrees Celsius to make metallurgical-grade silicon. That product carries impurities. To reach solar-grade purity, manufacturers use chemical routes. The common path is a hydrochlorination and deposition loop, producing trichlorosilane and then decomposing it to form high-purity polysilicon. These reactors operate at high temperatures and tight chemistry control. Purity targets are extreme. Impurities must be measured in parts per billion because a single heavy atom can become a recombination center and kill efficiency. After polysilicon, the next conversion is melting and crystal growth. For monocrystalline cells, we add controlled dopants such as boron or phosphorus to set a baseline conductivity. For multicrystalline, molten silicon is cooled in molds to form many grains. At every step, vacuum chambers, inert gases, and chemical scrubbing systems remove contaminants. Think of this stage as metallurgy at surgical precision. You melt, filter, and deposit atoms until the raw material is a clean sheet ready to host electrons for decades. Turning polysilicon into wafers is a precision thermal ballet. The signature technique for monocrystalline material is the Czochralski process. A crucible holds molten silicon at roughly 1,420 degrees Celsius. A seated crystal dips in, then rotates and very slowly lifts. The result is a single crystal ingot, oriented to crystal axes, millimeters per minute at the growth front. For multicrystalline, molds cast blocks that cool into many crystal grains. The ingot then faces the saw. Diamond wire saws slice the rod into wafers only 150 micrometers thick, with kerf losses minimized by technology that recovers slurry and reclaims diamond grit. Each slice is a flat, mirror-like disc, but still far from a finished cell. Edge chipping, subsurface damage, and microcracks must be removed. Grinding and chemical-mechanical polishing produce smooth surfaces while preserving thickness. Manufacturers balance thinness for material savings against mechanical strength. At this stage, precision is literal. A few micrometers of variation changes breakage rates and electrical performance. The wafer is now a blank canvas for doping, texturing, and coating. A bare wafer will lose most light to reflection and recombination. The next act is surface engineering and junction formation. First, manufacturers texture the front surface in an acid or alkali etch that forms microscopic pyramids or inverted cones. These nanostructures trap light, increasing the path length by multiple bounces. Next comes doping to make the emitter. The standard method is a diffusion furnace. Wafers enter a quartz tube, heated to roughly 800 to 900 degrees Celsius, while a dopant gas such as phosphorus is introduced. Phosphorus atoms diffuse into the silicon surface, creating a thin, highly doped layer on the order of a fraction of a micrometer. The target sheet resistance is engineered, commonly around 60 to 80 ohms per square, balancing conductivity and optical losses. For high-end lines, ion implantation achieves tighter profiles, followed by rapid thermal annealing that activates dopants in seconds. This created PN junction is the heart of the cell. It establishes the electric field that separates photo-generated carriers. Imagine sculpting a razor-thin hill on the surface that repels electrons in one direction and lets holes flow the other way. A solar cell must hold on to every photon it can. Even with texturing, bare silicon reflects a significant fraction of sunlight. The antidote is an anti-reflective coating deposited by plasma-enhanced chemical vapor deposition. A common film is silicon nitride, laid down at roughly 300 to 400 degrees Celsius to a thickness of about 70 to 80 nanometers. This film does two jobs. It reduces reflection across the visible spectrum and provides a partial chemical passivation. For advanced passivation, manufacturers add a thin oxide layer or aluminum oxide on the rear, and sometimes a silicon nitride plus hafnium or titanium stock. These layers reduce surface recombination velocity by protecting dangling bonds and creating field effects that keep carriers away from the surface. Passivation boosts open circuit voltage, literally raising the potential of the cell. At this scale, tiny chemical bonds control efficiency. Think of coatings as sunscreen and insulation for atoms. They keep photons working for you and carriers from leaking away. A cell that generates charge still needs highways to move current off the surface. Metallization is the act of printing those highways. The front contact pattern is screen printed using a silver paste and fine mesh screens that define fingers only a few dozen to 100 micrometers wide. Behind the scenes, paste chemistry includes glass frit that etches a path through the passivation and forms a welded contact to silicon during firing. Wafers run through a belt furnace where rapid heating produces a peak of around 700 degrees Celsius for a few seconds, sintering the metal into conductive tracks. The back receives an aluminum paste to form the back surface field and a low resistance contact. Newer lines use plated copper or copper on nickel to reduce silver usage, requiring electroplating baths and additional thermal steps. Finger spacing, finger width, and bus bar count are engineered to balance shading losses and series resistance. The result is an intricate metal lace visible to the eye that must bond reliably across millions of thermal cycles. After processing, every cell must prove its numbers. Quality control begins with flash testing. A xenon lamp simulates the solar spectrum and delivers 1 sun of intensity, while sensors capture 3 critical values: short circuit current, open circuit voltage, and the maximum power point. From these, technicians compute the fill factor and conversion efficiency. Cells are binned by performance. Those with microcrocks, shunts, or low VOC move to lower tiers. Electroluminescence imaging is the next microscope. Apply a forward bias and the cell emits faint infrared light where carriers recombine. EL reveals crocks, hidden shunts, and broken fingers invisible to the eye. Thermal imaging catches hotspots under load. Statistical process control logs distribution shifts and pinpoints drift in furnaces or coating chambers. These diagnostics are not cosmetic. A 3% efficiency variance in a production lot translates to tons of lost energy over the module lifetime. Testing converts anecdote into data, and data governs the line. A single cell is fragile and low in voltage. To make panels, manufacturers string cells in series and encapsulate them into a durable package. Automated tabbing machines solder thin copper ribbons to metal fingers, forming strings of cells that are then laid into an array on a polymer sheet. The stack typically goes tempered low iron glass on the front, an encapsulant such as ethylene vinyl acetate, the cell strings, a back sheet often of polymer composite, and then an aluminum frame. This sandwich moves into a lamination press. Under vacuum, the module is heated to roughly 150 degrees Celsius and pressed for 10 to 20 minutes. The encapsulant flows and cures, bonding glass to cells and removing trapped air that would otherwise cause delamination. A junction box is affixed and electrical connections are routed. The module is now weatherproof, ready to be mounted on racks or assembled into arrays. Mechanics, chemistry, and heat meet here to create a long-lived energy product. Solar modules live outside and must endure years of storms, UV, and temperature swings. Testing protocols are rigorous. Thermal cycling exposes modules to repeated swings from below freezing to hot daytime conditions, often from negative 40 degrees Celsius to 85 degrees Celsius, checking for solder fatigue and delamination. Damp heat chambers hold modules at 85 degrees Celsius with 85% relative humidity for 1,000 hours, forcing moisture to reveal weak seals and ionic migration. Mechanical load tests apply pressure equivalent to heavy snow or wind, commonly 2,400 pascals or more. Ultraviolet exposure chambers accelerate light-induced degradation. Potential-induced degradation tests apply voltage bias under heat and humidity to check for leakage. Each failure mode is documented with electroluminescence, infrared imaging, and visual inspection. Manufacturers run these tests on sample modules and push line adjustments when anomalies appear. Passing these trials is not bureaucratic. It is the difference between a panel that generates power for 25 years and one that does not. After passing tests, modules roll off the line and into arrays that convert sunlight into usable electricity. Installation is the last engineered step. Racks are angled to optimize incident light, wiring reduces resistive losses, and inverters translate direct current to grid-ready alternating current. Performance in the field is tracked. Manufacturers expect initial degradation of a fraction of a percent per year. Common guarantees predict roughly 0.5% to 1% annual loss. Recycling and end-of-life are also engineering problems. Recovering glass, aluminum, and silicon requires thermal or mechanical separation processes and is becoming a standard part of the life cycle. Meanwhile, cell technology continues to evolve. PERC, heterojunction, TOPCon, and tandem designs push efficiencies higher by changing passivation strategies, adding thin films, or stacking materials with different band gaps. But the core logic remains: transform ordinary atoms into a lattice that captures photons, control where carriers go, and extract usable current without loss. From sand to sun, the journey is a cascade of heat, chemistry, and microscopic precision, engineering that turns light into power. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.